So I just wanted to review solving for an unknown exponent, but we're also going to review the compound interest formula when we do this. So compound interest is an exponential relationship. When I talk about compound interest, I earn interest on the principal value or the amount that I put in, and I also earn interest on previous interest, which makes it exponential. Here's the formula for compound interest. Okay, and this is just like a very simple, straightforward compound interest type question. Last year we learned about different compounding periods, like compounded semi-annually, compounded monthly, all of that good stuff. We're just going to do compounded annually, so once a year for this one, so straightforward. So P represents sort of kind of like what A represents in our y equals A times B to the x formula. So P is going to be your principal value. I always forget whether it's AL or LE for principal. I think it would be LE in this case. Principal, yeah. Principal value, so that's the initial value, 500. A is our future value. Do we know what the future value is in this question? Zach? So is that the future amount of money, though? No? Sir, what? Why? Why is it 1,000? Okay, so I want to know when 500 becomes $1,000 then, right? So that's the future value. Do I know I? Interest rate as a decimal. Sarwa? Yes. So if I switch 7% into a decimal, 0.07. And n usually has like two components, right? But because this is compounded annually, n is just really, I compound once a year for a certain number of years, and n will end up being equal to the number of years. So n is going to be technically total time times the number of compounds per year, which is 1 annually. So n will end up equaling the total time in this case. Okay, so let's plug this into our formula. We have 1,000 equals the principal amount, 500. 1 plus 0.07 to the exponent n, which is also equal to total time. Okay, if you want to put n in there, you can put n equals t, so you can also put t if you'd like. Okay, so unknown in the exponent, I should be thinking log right away. Let me know, guys. I know, don't raise your hand if you were in my class last year. You better not. But if you were in Battering's class, did you guys learn log?
No.
Okay, because my other class, I asked my other class, and they were like, no, we didn't. So I realized once I asked my second class that that was probably new for you guys. So we'll practice it with this one. If you were in Michaelis's class, did you learn how to use log last year?
No.
Yes. Yes, okay, good. Okay, so in order to use log, so basically in grade 11 I introduced the idea of we use log to isolate for an exponent. That's basically all we knew of log in grade 11. So make sure you have your own calculator because we're going to want to make sure we know how to use our specific calculator for this. When you use log, it's used only when the unknown is in the exponent. Also, the base and the exponent must be isolated on one side. So in order to start questions like these, we need to make sure any other values are moved over to the other side. So in this case, we will divide out 500 to start. And I'm also just going to add the 1 and the 0.07. So it'll be 1.07 to the exponent n. Now that the base and the exponent are isolated on one side, then because it's kind of hard to figure out what that exponent might be, I'd have to do a lot of guessing and checking here. That would be tough. Log is what helps us with that. So we are going to take the log of both sides, because what I do to one side of the equation, I must also do to the other, right? We must make sure that the equation stays equivalent. And the nice little log rule that helps us isolate for an exponent, it's called power rule for logarithms. And it says that if I have the log of something to an exponent, I get to take that exponent and move it in front of that logarithm as a multiple, okay? I just told my grade 11s, I'm like, just trust me, it works. But we'll explore a little bit more like why this is true, and it's connected to the idea of logarithms and exponentials being inverses, right? So we're going to have log 2 equals n times the log of 1.07. You can put it in brackets, you can drop the brackets, it doesn't matter, it's just a single value. And then I just need to get the n by itself. So if I'm doing n times the log of 1.07, what can I do to get n by itself? Bella? Okay. So no calculators needed at this point, right? This is all by hand. We don't need our calculator until the very end. So these are canceled now, and n should be equal to the log of 2 divided by the log of 1.07. So let's all try that in our calculators. The really important thing that I highlighted last time that maybe you were too confused at this point to care about is if your calculator opens a bracket on after you put log in, you must close that bracket before you divide by the log of 1.07. So this is the important piece here, is you're always going to make sure that you are putting brackets or closing up brackets if they're opened up by your calculator. Okay? So what do we get? What should we get? Hey, also guys, if you have that blue calculator that has orange buttons, it's like black with blue and orange. I think there's a couple other versions of it as well. You guys might have this button as well. I don't want that button. I want just the regular log button. So you might have to search for that a little bit. If you can't find it, let me know. I can help you, okay? Okay, so what should we get from this? Michael, what'd you get? Sarah, did you get the same thing? Yeah. Okay. And this is yours. We'll leave the, is it 10.245 exactly, or was there more? Okay. Okay, so we'll just round to 3 then, that's fine. Okay, so therefore, after 10.245 years, you could change the decimal into months if you wanted to, don't need to. There will be $1,000 in the account. All right, so this is our recap, but also kind of like a reintroduction or maybe just a new rule for you guys. This is called power law of logarithms. And the power law of logarithms says that if I have the log of any base, so a lot of times when we're doing our solving process, I just use the regular log. What do we know the base is of any logarithm if I don't see the base? Remember we talked about there's an understood thing there? Like to see all those hands. Keaton? 10. Okay, so the base that's understood there is 10. So we are using a base, but it could be log with any base. It doesn't have to necessarily just be the common logarithm. It could be literally anything. But power law says, can you grab the back door for us there? Thank you. Power law says if I have the log of any base, b, to x, and the x has an exponent of n on it, it says I'm allowed to take that down and write it as a multiple. Okay? This is also provided that b, the base, is positive and not equal to 1 and also that x is greater than 0, because we know the domain of a logarithm is not defined for negative or 0 numbers. Part of this actually comes from, so we talked about how logarithms and exponentials are inverses, right? What do I do when I have an exponent on an exponent? We reviewed this last lesson. What happens when I have x to the a to the b? Kenzie, what do we do? We multiply the exponents. And what's the answer to any logarithm? Logarithms give me out the answer that is an exponent. Okay, so if this is an exponent, and this is an exponent, and when I look at the exponential version of this, I keep the base and multiply the exponents. If the logarithm is an exponent, and I have an exponent on an exponent, it makes sense that we can write this as a multiple, right? Because it's exponent rules, okay? So if you didn't understand that, just memorize the rule, you'll be fine. But that's what it's connected to. It's connected back to exponent rules. So we can write it as a multiple. We're basically multiplying the two exponents. The log is an exponent and the n is an exponent. We multiply it together. Okay? So if I were to go and evaluate this, rather than doing 8 to the 5 in my calculator, I'm going to use power rule, which says that instead of doing the exponent part, I can actually, if I have the log of any base to an exponent, I can actually take that exponent and parachute it down and write it as a multiple, right? So we're going to bring it down, write it as a multiple. Okay, this is power rule. And does anyone remember what this is asking me? Log base 2 of 8. What is the question that this is asking? Keaton?
Is it what to the power of 2 equals 8?
Close. It's 2 to the power what equals 8. But I think that's what you were trying to say. So 2 to what exponent equals 8? 3. So that's the answer to the logarithm. So this will be 5 times 3. Okay, so just as a side note here, the question is 2 to what exponent equals 8? The answer is 3. 2 to the exponent 3 equals 8. So that's why the answer to this logarithm is 3. Okay, and 5 times 3 is, of course, 15. Okay, no calculator needed for that one, right? Okay, we recapped this last lesson. How do I express a root as an exponent? What is a square root as an exponent? Bella? 1/2, okay. The reason for this is, just as a reminder, one more reminder here, is because I have an understood exponent of 1 on there, and an understood sort of like 2 in front of a square root. If I don't see the number, we assume it's a square root rather than a cube root, 4th root, 5th root. And then I do 1 over 2 to get that rational exponent there, okay? So it doesn't matter what numbers are there. You'll always do whatever this is over whatever is outside. Okay, we just understand that there's a 1 and 2 there when we see a square root. Okay, so I have a log to an exponent. I'm going to bring the exponent down as a multiple using power rule. And I want to know, so we can do some guess and check on our calculator maybe. So let's try some different exponents on 7. So we need to know 7 to what exponent gives us 343. No need to use the log button here at all. Just try some different exponents on 7. Kenzie, what'd you find? 3? Got the same thing, Keaton? Okay, so we have 1 over 2 times 3, and that would give us 3 over 2. Questions so far? Anything I can clarify? So if you have log base 2 of 8, what we practiced is, not yesterday, but 2 days ago, we practiced expressing 8 as a base of 2. So if these bases are the same, this is log base 2 to the 3, right? If we replace 8 with that, and then the answer will just be the exponent, because if I take the 3 down using power rule, and I have log base 2 of 2, so as long as these are the same, the answer is just the exponent, because 2 raised to what exponent gives us itself? 1, right? 2 to the 1 gives us back 2. So this whole thing just becomes 1, and that's why the answer is just the exponent. I think that's what you're asking me about, right? So that's only in the case where we can make these two bases the same, when I can make 2 and 2. So I would have to express that as a base. So I could have done that for this one. Like we could have essentially just done, like I could have added an extra step here, and we could have written this as 7 to the 3. And then the answer to that whole thing, because I made those bases the same, is just 3, right? So I'm just sort of skipping over that step today, because we're just thinking about what's the answer. Does that make sense? Okay. Okay, so we don't need this. I'll erase that. Any other questions? Kenzie?
Is it ever possible that you need to have it with a, like a number with 7 people?
Okay, good question. So is it ever possible that we would have a base, whoops, I'm on the eraser, that I would have a base that does not go into this? For instance, like 7 to a whole exponent will not equal this. Yes. And that's where our calculators come into play, because I don't want to guess and check a bunch of decimals. So yes, it is possible. Good question. Okay, so last class we learned about something called the change of base formula, and we just said, like, hang tight for now. We'll talk about this after. But the change of base formula can sort of help us because, and this actually goes straight to your question, Kenzie, because 7 to a whole exponent equals 343, and 2 to a whole exponent equals 8. But what if that's not possible? So what if I have something like 4 equals 1.2 to the x? I already have a decimal. That makes things more complex, right, to try and find that exponent on there. So normally what we would do with power law is we would take the log of both sides, right, because the base and the exponent are already isolated. So I would log both sides. And power law says because I have the log of something to an exponent, I can take this exponent and start bringing it down in front. Guys, please don't start bringing exponents down unless you have logarithms in front of them, okay? I started to have, like, sometimes I'll start to have people that are like, oh, I'll just bring the exponent down, like in something like this. They'll be like, oh, it's 4 equals x times 1.2. No. Only if you have a logarithm in front, okay? This is a specific log rule where we have to have a log of something to an exponent. Then we bring the exponent down. Okay, so I will bring the exponent down. I will have x times the log of 1.2. And then what would we do? We would just, Matt?
You just divide it by log 1 over 2.
Yeah. Okay, perfect. So enter that into your calculator, guys. Remembering that if my calculator opens a bracket here, I will close it to calculate. If you're getting the wrong answer, that is most likely the reason why. What'd you get, Matt?
7.603.
7.603. Anyone else?
How many decimal points do you list?
Let's go thousands. We'll do 3 decimals. So does it round up?
604.
Okay. Okay. Everyone else got the same thing though? Okay. 7.604. Okay, how can I check my answer? M? Plug it back in. Because we rounded, it will be slightly off, right? But it should be something very, 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 very close to 4. The more decimals you leave on this, the closer you'll be once you plug it back in, okay? But it might be like 3.999 something, I don't know. But yeah, plug back in to check. Okay, so that's the nice thing is plug in to check. you will know if you're right or not. I can do the same thing in my like exponential questions too, right? Like I could have done that back in question number 1. If I take this and I sub it in for n here, I would check that this is equal to 1,000, right? So I should be able to do that for any question where I solve. I can plug back in and double check. Okay, so with the change of base formula, if I have something like this, log 4 over log 1.2, we talked about the change of base formula, and the change of base formula said that if I have log of 4 over log of 1.2 equals x, one way that I can condense this into a single logarithm is I can write log base 1.2 of 4. This is the change of base formula. And we can also get that from switching into logarithmic form from this, right? If I were to switch from exponential right into logarithmic form, we know that as we switch this, it's log base 1.2 of 4 equals the exponent x, right? We practiced this in our homework from the last thing. So how do I calculate this? How do I calculate something like this? So on the one hand, if I switch this into logarithmic form, I will get this. And on the other hand, if I have something like this, using the change of base formula, those two things are equal, right? I get log base 1.2 of 4 equals x. So let's practice putting this into our calculator. One way that we can put this into our calculator, and this is going to be for the majority of you guys, is we use the change of base formula to write this as the log of 4 over the log of 1.2. And then we'll calculate it the same way that we did this. Some of you guys have a button that looks like this. And it's the people that have that black calculator with the blue and orange buttons. If you have that button, you can actually evaluate this in your calculator. You can actually just press that button, and then you can fill in the boxes. Most of you guys just have a regular log button. So you can't calculate something like this. You have to switch it into this format first, and then you have to do log of 4 over log of 1.2. Okay, that's why the change of base formula is important, is that we understand how to switch between something expressed as log base 1.2 of 4 and switch it into a division of logarithms. Okay, so so that will be for the majority of you. You will have to switch it into this form and then use just your regular log button to do log 4 over log 1.2. Anytime you want to evaluate a logarithm, such as log 1.2 of 4, you can use the change of base formula. And the change of base formula is exactly what I explained to you guys above. So if I have log base b of a, I can calculate this by doing log of a over log of b. Okay? And in fact, it actually does not matter what the base is. So if I wanted, usually we would be using the common logarithm for this because that's what's stored in our calculator. But any base is actually possible. This will be equivalent. I can actually choose any base there. So long as everything is greater than 0, and b and m aren't equal to 1. This will be true. So using this formula, we can determine that log base 1.2 of 4, as I wrote above, is log of 4 over log of 1.2. And that's exactly what we calculated when we used power law. So it's just sort of like two different ways to calculate when you're solving an exponential expression. Okay, it's also the way that you're going to calculate any logarithm in your calculator if you don't have this log button. But even if you have this log button, you need to know this rule. Okay, so you should know how to use the regular log button or that log with the little box button. Okay, so if I were to evaluate log base 6 of 23, I don't need to use that log square button on my calculator. All I need to do is I can switch this into log 23 divided by log 6 using change of base. And then I just plug it into my calculator and calculate. So this is a good example of Kenzie's question because 6 to 1, what exponent equals 23? I don't know. I don't know off the top of my head, right? It could be, it's probably between, like 6 to the 2 is 36, 6 to the 1 is 6. It's between 1 and 2. I don't know. 1.7, something like that. What did you get? Oh, I guessed it right. 1.76? 1.75. Okay, how about this one? How would I calculate, or how do I use change of base? And then I can plug it into my calculator. So how would I switch this into log of something divided by log of something? Zach?
Is it log 14 over log 1/2?
Yep. And then we plug into our calculators. So this will tell me half raised to what exponent equals 14. It's going to be a negative exponent. Serena?
It'd be negative 3.81.
Yeah, everyone else got the same thing? Okay. We can check by doing 1/2 to the exponent negative 3.81 and see if we get something close to 14. Okay, so same thing here. I check that 6 to the exponent 1.75 is approximately equal to, not 33, 23. Okay, same thing here. We check that 1/2 to the exponent negative 3.81 is approximately equal to 14. Okay, it might be off slightly because if we round those decimals, then we're rounding an exponent. So you might get something a little bit off from that. Okay, so let's solve in two ways. So let's say we'll split this into two. We're going to do a method 1, and we'll do method 2. And I'm going to use the ways that we just talked about above. Method 1 is going to be, we'll use power law. So with method 1, this is like our classic method that we've been sort of reviewing. Some of us are learning for the first time. But we will take the log of both sides. And I can do this right away because 2 to the y is alone on one side. It doesn't have anything else with it. Otherwise, I would take a step to move things. Using power law, now I have the log of something to an exponent. I will take that exponent and parachute it down in front here, and we can write it as a multiple. So it's y times the log of 2. And then I just divide out log 2. Okay, so log 100 divide log 2. What do we get? Emma? Okay, a couple people confirm for me. I see thumbs up, that's good. Okay, that's the first method. Second method is, I want to take this, and I want to express this in logarithmic form. So remember we practiced in our first lesson in our homework, switching back and forth. So how do I express this in logarithmic form? Amelia?
Log 2 100, and then log 100,
Equals y, right?
yeah, and then log 100 divided by log 2.
Okay, so we switch the form, switch into logarithmic form. And then we use the change of base formula. So I know I can evaluate log base 2 of 100 by doing log of 100 over log 2. Andrew?
What's that method called?
This would just be switching between the forms and then change of base. So we can call the, I guess we can say we'll use change of base for this. That's the rule that we would be using. Okay, and then of course we should get the same thing because this calculation ends up being the exact same as this one, right? So just two different ways to solve here. this one is power law. It's basically the same number of steps, it's just whatever you feel more confident doing. Either way, you'll get to this point. Any questions on this? Okay, we are going to do 2 quick applications here, similar to our grade 11 stuff, but I'm going to use maybe our new method. Maybe we'll try out our new method to solve. So population of a town is currently 78,322 people. Population grows on average by 3% per year. When will the population of the town reach 150,000? So I'm going to use the exponential formula. This will be a nice little review for us, how we do growth by 3%, how we figure out our b value from that. Okay, so somebody give me one piece of information. What do we know out of y, a, b, and x? Keaton.
Y is 150,000.
Okay, future value is 150,000. What else? Emma? Okay. 78,322, that's the current population or starting population. Zach?
I is 0.03.
Okay, so if we were doing interest, we would go and use compound interest. So we do need to think about the 3 in terms of a decimal. What else do we need to do with this, Bella?
1.03
Okay. So growth by 3% is 100% of what we started with, plus an additional 3%. So I want to make sure that I put 103% as a decimal. If it were declining by 3%, I would take 100 and I would subtract 3 from it. That's the only reason why I don't use the compound interest formula for these, because sometimes it's growing, but sometimes it's losing that percentage, right? So we need to understand that we take 100% of what we have and we add the growth or subtract the decay, right? And then switch into decimal format. What pieces of x do we know, if any? Remember, x is total time over time for one growth or decay to happen. Serena?
It happens like per year, so the bottom part would be like over 1.
Okay, so over 1 year. And do we know the total time? Okay, so that will just be t. So in the end, x will be equal to t. And I will get t out in years. Okay, so let's plug into our formula here. We have 150,000 equals 78,332 times 1.03 to the exponent t. In any case, guys, I don't use either of these methods until the base and the exponent are alone on one side. So I always have to start by making sure that the base and the exponent are alone, which they're not right now, right? Where did I put my calculator? There it is. Okay, so let's start by dividing that 78,322 out. If you don't get a whole number from doing 150,000 divided by 78,322, you're going to leave in fraction form. Because the more I start to round things, the more of a problem it becomes when I try to find the actual like exact answer. Okay, so fraction form, this is a repeating decimal, so I'm leaving it as this. Now we have 150,000 over 78,322, and that's equal to 1.03 to the t. Now, you guys, so if you had battering last year, you use either method, whichever method you feel more comfortable with. I just showed you 2 methods above. If you had me last year, I want you guys to try this method, because this is a new method for us. Okay, so I'm going to give you guys a couple seconds. Choose a method that you want to go with, and see if you can solve from here. So you either need to use power law, or you need to switch into logarithmic form and then use change of base. He reminded me that I wasn't recording. That would have been bad. Positions are open for second favorite. Okay, so I used the switching format. So we switched from exponential into logarithmic form. Then I used change of base. So log of this over log of the base. You should have gotten this no matter which way you used. If you used power rule, you would have logged both sides. You would have brought the t down, and then you would have divided out the log of 1.03. So either way, you would have ended up at this point. Any questions? Anything I can clarify here? Sam?
So what's the point of switching into the log form? You just end up in the same place.
Well, I'm just showing you guys two methods. So I just wanted you guys to practice that second method. Okay, yeah, Emma?
On the test, can you choose from like you do?
I might ask you, show me two ways to solve this. So you would need to know both, right? It would reach 150,000 people by 21.98 years. Regardless of whether we feel more comfortable with the other method versus this method, we will still have to use the change of base formula for like a variety of different things and stuff like that. And we will have to switch between logarithmic form and exponential form. So like we still need to know how each component of this works. So either way, like even if I said solve how you want, there will be other questions where you'll have to use these skills in them. So it's good to practice the skills anyways. Okay, last one, and then you guys will have about 25 minutes to work here. So the value of the average vehicle decreases by 18% per year. If an SUV is purchased for $45,000, when will its value be $12,250? I'm going to use the same formula, the exponential formula. What do we know? Keaton, give me one thing.
Y equals 12,250.
Okay, future value is 12,250. Serena, give me another.
And it's 45,000.
Initial value, $45,000. What else? Kenzie? Okay, 0.82 for B. Where does that come from? Amelia? Mm-hmm. Okay, so decrease by 18%. That means that every year, 82% of the value will remain from before, right? So I need to express B as 0.82. Okay, and what components do we know for X? We should know some pieces of this at least. Or one, we would need to know one piece in order to solve. Sirwa?
It's per year, so it's T over 1.
Okay, T over 1 year because it's per year. So I'll get T out in years when I solve this. Okay, let's plug in. In either method, we must have the base and exponent isolated on one side, so you're going to divide out the 45,000 to start. Okay, this is a repeating decimal, which means we are keeping this in fraction form. Emma?
Can you, like, if it gives you a reduced fraction, can you use that one smaller?
Yeah, yeah. Some of your calculators, yeah, I know they will spit out like a reduced fraction. If you want to use that, that's fine. But the decimal was a repetitive, like it just kept going forever, so leave in fraction form in those cases. You can use either method from here. We can switch into logarithmic form and then use change of base, or you can log both sides, bring the t down using power rule, and then go from there. Okay, so choose a method that you want to try. I'll give you guys a couple seconds. Maybe I'll write both methods just for what you want to choose. Got to record. Method 1, power law. So if you practice power law, we log both sides. We parachute that t down in front as a multiple, and then we divide out the log of 0.82. Method 2, change of base. We take this, we express in logarithmic form. This is log base 0.82 of 12,250 over 45,000. That's equal to t. And then t equals the log of 12,250 over 45,000 over log of the base, which is log of 0.82. Either way, we end up at this point. Okay? So sorry, Jake, what did you say? 6.65?
Yeah, oh, it's 0.56.
6.56. Okay? And this tells us what? Kenzie? We'll just leave it. Yep. Yeah. Okay, so in 6.65 years, it takes 6.65 years to, what do I want to say, decrease to 12,250. Okay, I want to encourage, if you feel more comfortable with one method over the other method, when you're practicing, choose the method you feel more uncomfortable with, because that will allow you to practice that method and get better at it. If I always choose the one that I feel most comfortable with, then I'm never practicing the stuff that I need work on, okay? So choose a method that you feel most comfortable with when you're doing some practice questions, or if you don't feel super comfortable with either, choose a mixture of both as you're doing your work, okay?